I'm Dan Roswood with Avnet Technical Marketing.
Speak up.
I'm Dan Roswood with Avnet Technical Marketing, and designed a system for to demonstrate sensor fusion. If you take a look down here, we have an example system that was constructed based on working with an expert in the plastics industry. Starting on this side, we have our digital isolated inputs, whether it be analog or digital. These inputs are used to control the machine, such as e-stop, starting, stopping, things like that. As part of the plastics industry, your media is taken in a different area. It's actually held outside the material that you're going to melt. So we have a remote sense here, which is current-based, and that's used to determine how long we need to manipulate the material inside our factory in order to prep it for use within the extrusion machine. Here we have an example of an ultrasonic sensor. It's a cheap sensor, but the story behind it is that we're using it to show how easy it is to use the Zynq tools to take a C code and bring it into the fabric and hardware accelerate. This here is an RTD. It's by Measurement Specialties. It's nickel-based. It's used in conjunction with the current sensor in order to sense the temperature of the materials. Since plastic extrusion deals with high pressure and various temperatures, we wanted to also sense the ambient pressure around the machines. So this is a free-scale pressure transducer that can give us a 50 kilopascal to 115 kilopascal reading at a plus minus 1 kilopascal. That's about what was that? It's about a half an atmosphere to about 16 psi. So it's a pretty wide range, very accurate, and gives us a very good reading so that we can start tracking that for trending reasons. Coming back over to here, as part of this story, we're trying to demonstrate that you can do a sensor fusion yourself. Sensor fusion being you put in 3 things and you can actually get 4 things worth of information out. So more information can be extrapolated by combining various information. So what we have here is a quad thermocouple input that's made by Analog Devices. And right now on the demo, I'm just measuring the temperature of the Zynq chip. However, in the story, we're actually using that to measure the temperature of the front bearing, the rear bearing, the motor coil temperature itself, as well as the ambient temperature around the machine. The reason that you need the ambient temperature around the machine itself is each machine within your factory is going to have a different ambient temperature due to the high extreme temperatures used to melt the plastic material. The next item I have here is also by Analog Devices. It uses an accelerometer that we've attached up here to the servo motor. That accelerometer is sensed and converted into a frequency. Using this, we can tell what the frequency profile of our motor is. Depending on the various process, the frequency has been shown to be very consistent depending on the material that we put in there. So by using this, we can tell when the machine is going to start having problems because the vibration is going to start changing. However, we can also extrapolate based on temperature what's wrong, whether it's the process itself, the motor, the entire machine is shaking, or that a bearing is starting to go bad. A bearing is starting to rise in temperature versus the vibration. We now can tell exactly where the problem is going to be. Also, as part of the story, we want to know how much current the system is using. A typical problem with the plastics industry is the motors used drive a lot of power. So if you're in a country that doesn't have a very reliable grid or power system, you could actually be running in a brownout condition and not even know. Well, by using this with a temperature sensor, we can tell when we're in an overcurrent situation because we have bad power coming in. We're measuring current here. This particular unit only does a 5 to 6 volt measurement. However, ADI has an entire family of these that will read the voltage level that you need for your needs. Basically, they have a 230 volt unit and they have a 500 volt unit. And I think there's one more. Check their website. They have a very wide selection of other products on there. Over here we have a MR sensor. It basically, in this example, I'm using a magnet here, and as this unit actually spins, it'll spin around, and as you might be aware, a magnet has a field that's kind of a donut shape. Well, as this actually spins around, this magnet will actually pick up that field. So the idea would be you would attach this magnet to the end of the motor, and actually measure and sense that as it's turning. The next item I put on here is an inductive sense. The reason is, in the plastics industry, you tend to have a very large motor. It's coupled to a very large screw. The screw is turned in order to create the pressure and the temperature compression that you need for the material that you're melting. I wanted to know, because the screw is actually a maintenance item that gets removed out of the machine and recoupled in to the motor, I wanted to know that the mechanical crew actually reattached the motor to the screw properly. The issue became, my plastics expert and I were talking, and I said, well, we can drill a hole through the machine and add a sensor in so that we can actually measure the system turning. However, due to the pressures, which I was not aware, and the temperatures, and also the possibility for contamination of the material, that was a no-no. So I had to kind of look at, well, how can we do this wirelessly without attaching anything to the screw, doing anything to the machine itself? And what I ended up using was this part here, which is an LDC 1000 by TI. It's an inductive sense. This coil here emanates a field, and actually as this spins around, it picks up the aluminum foil here as it turns. I've been asked that, well, doesn't actually just putting this against the base of the machine have a problem? Well, because it's more of an AC coupled type sense, once it gets placed on the machine, it really won't see the machine anymore. It's only going to see the screw, because as the thread of the screw turns and passes over the sensor head, it'll actually create just a square wave to say the thread is actually going. So now we can monitor, knowing the pitch of the screw, we know how many threads per inch, and we can actually calculate the rotation of the screw to guarantee that the rotation of the screw matches the rotation of the motor. So again, sensor fusion, putting two sensors together or more, coupling against each other so we can determine better information about our system. This helps us with our preventative maintenance issues, it helps us schedule those, and helps keep us closer to a 24/7, 365 uptime, which is what all factories are striving for at this point.
Okay, so ultimately this all couples into a Zynq, right?
It does.
Okay.
So, knowing that this entire system here is doing this, you can see we have a touch screen here, we have a Wi-Fi connected, and the actual physical buttons. And you notice that everything kind of emanates towards the center here. The center focus, as I said before, is we've got this thermocouple that comes down and touches our Zynq here. Using this Zynq, we can leverage having all of this sensor fusion occurring in complete, true parallel processing to our screen and our interface to our people. The screen, using the PS or the dual arm core system, will actually run our software, our connection back to our main database, our cloud. However, using this FPGA fabric, we're able to use that to perform any FFTs or any sort of pre-processing that we need in order to just provide basic information to our user and back to our management, back to our system and our cloud as a whole. So it provides a very, very well thought out and a great example of a system, allowing a great flexibility to be able to interchange anything you want. All the devices you've seen here are just SPI. However, there's nothing saying it couldn't be Bluetooth, Bluetooth Low Energy, it could be Wi-Fi, it could be I2C, or any other custom protocol that you might need for your system, all because the flexibility, the programmability of the programmable logic that's within the Zynq part.
Great, thanks very much.
Absolutely.